I believe you're doing amazing and welcome to this first Principal Thinking YouTube channel. And this is part 6 on permanent magnet material. And here we are going to discuss about BH curve of permanent magnet. And if you have not watched all the previous video, I request you to please go back and watch it and then come back to this video. So, before I talk about BH curve of permanent magnet, let me tell you about a story of a David who has a real batting talent, stance and the skill, but when it comes to the big game, he get out after playing just 1 or 2 ball, and you know why. Because he was not having any coach to guide him. David realized he need help after countless failure, so he started seeking coach once a month. Surprisingly, his game improved drastically after just one coaching session, but he wasn't at the top, and so he started going twice a month. And you won't believe it, but his performance went up again, so he thought why not 3 times a month, and yep, his game got even better. He kept increasing his coaching session until he was practically living at the coaching center and he was playing like a pro, but then his coach has to leave for another project. Without his mentor, David's batting performance started declining. He started taking even alcohol and his game suffered. He went from top scorer to struggling to even make a decent run. Eventually, he got kicked out of the team and it was real low point for him. But after 2 long years, his coach returned and was shocked to see him, and he asked, "What happened to you? You were the top batsman." And that was the wake-up call for the David. He got back on the field and started training again with his coach. And guess, he climbed right back on the top and showing everyone that talent alone isn't enough. You need someone to guide you if you want to be the best. So yeah, the moral of the story is skill only takes you so far, but you need a mentor or a coach to reach at the top. Similarly, like a David, there are certain material in the nature which has God-gifted ability to attract or repel another ferromagnetic material even without touching them. But this material attract or repel only if it is activated using an external means, and that external means is H field or a coach, what we are talking here. What is BH curve? In a very simple term, we are checking the ability of material to attract or repel at a different external field condition. And that ability is called B field or magnetic flux density, and that external field is called H field, produced by an external coil carrying current. This classical formula we already know it, where B is the resultant of magnetic field generated by unpaired spinning electron plus external magnetic field if at all it exists. And you might be asking why I am talking about this formula, because we are definitely going to plot the graph of B versus H, but along with this we are also going to plot the graph of magnetic moment per unit volume versus H. But wait, now if we arrange the equation, we can get this mu naught times magnetic moment per unit volume is equal to B field minus mu naught times H field. But magnetic moment per unit volume is having different unit than B field, because the unit of magnetic moment per unit volume is ampere per meter. However, unit of B field is Tesla. Because we are going to use same y-axis for B field and magnetic moment per unit volume, and hence we need to have a same unit. And we know that mu naught times magnetic moment per unit volume is having same unit of B field, which is in Tesla, and hence mu naught times magnetic moment per unit volume has been given an another name called J, which is magnetic polarization, and its unit is same as the B field in Tesla. So finally we are going to plot J versus H graph and B versus H graph. Now our aim is to plot B versus H graph and J versus H graph. How can we plot this? Is there any standard or guideline to plot this curve? And the answer is yes. The International Electrotechnical Commission, which is IEC, is an organization that creates and publishes this kind of a standard. And we are going to follow this standard, which is IEC 60404 Part 5. IEC 60404 Part 5 is an international standard that defines how to measure the magnetic field strength, magnetic polarization and magnetic flux density. This is the setup as per standard, where it has been kept at the room temperature 23 degrees Celsius, where the measurements are carried out in a closed loop magnetic circuit consisting of an electromagnet made of soft magnetic material and the test specimen, which is nothing but the magnet which we are about to measure. Now we need to measure B field and H field, right? How do we even measure it? And hence in this setup there are two instruments. One measure B field inside the magnet indicated by B, as you can see in this image, and the second one measure H field indicated by H. And we know that H is directly proportional to current I. We can increase and decrease the H field by increasing and decreasing the current. And now let's start measuring it. First, we are going to plot J versus H. Initially, J and H both are 0. Now start increasing H, J will start increasing along the dotted line, because domains will start aligning towards the H field. If we keep on increasing H value, there will be a point where all the domains are aligned, and if we increase H field further, J is going to be constant. Now let's decrease the H value and bring back to 0. Now what's going to happen on the J value? There will be no change or slight decrease in H value. In other words, domains are still in the same direction. Now further decrease the H value by reversing the current direction, and what we see, till the wide range of negative H, J value is going to be a constant. And if we keep on decreasing H value, there will be a point where suddenly the domains will flip to the opposite direction, where north pole becomes south pole and south pole becomes the north pole. And if we further decrease the H value, J value going to be a constant in negative direction. Now let's start increasing the H value and bring back to 0. Still, J value is going to be constant in negative direction. Now further increase in H value, and again what we see, till the wide range of positive H, the J value is going to be constant in negative direction. And if you keep on increasing, there will be a point where domain suddenly flip to the opposite direction, and this loop will keep on continuing, and there is a special name of this loop, and this loop is called hysteresis loop. Now let's draw B versus H, and it is very easy to plot. Just add J and mu times H field, and we will get the B versus H plot, which you can see in this image. When we bring back H field from its maximum value to 0, B field does not become 0. However, there is a residual B field even though H field is 0. And this is called remanence or residual magnetic flux density. Higher remanence value is always desired for any application like permanent magnet synchronous motor. Now when we keep decreasing the H field, there will be a negative H value where the first B field becomes 0 and then J will become 0. The negative H value where B field is 0 is called coercivity of magnetic flux density, and in this graph HCB is the coercivity of magnetic flux density, and the negative H value where J is 0 is called coercivity of magnetic polarization. It is also called intrinsic coercivity, and in this graph HCJ is the coercivity of magnetic polarization. Now let me ask you one question. Does the size and the shape of magnet affect the remanence and coercivity or not? In other words, let's say I plotted B versus H curve of this magnet material and we found the remanence and the coercivity. Now if we increase the size of magnet, then what will be the remanence and the coercivity of this bigger size of the magnet? Will it be same or different? Since remanence and the coercivity are being measured in the closed loop magnetic circuit, Therefore, size and the shape of magnet does not affect the remanence and the coercivity as long as it is measured in the closed loop, because J is equal to mu naught times magnetic moment per unit volume, and magnetic moment per unit volume will be same for any size and shape of the material, and hence remanence and the coercivity will be same for any size and shape of the material as long as it is measured in the closed loop magnetic circuit. Now let me ask you another question. Is there any benefit of higher coercivity? Let's say there is another material whose coercivity is Hc1b, which is higher than Hcb, and hence this material is going to resist higher opposing H field before becoming demagnetized, and this is the first benefit. The second benefit is higher the coercivity, thinner the magnet can be used for a given application. In permanent magnet synchronous motor, higher coercivity is always preferred because thinner magnet can be used and hence overall weight of the motor can be decreased. But wait, how can we prove this? Let's say we got the remanence value Br in a closed loop magnetic circuit. But once you create an air gap in closed loop magnetic circuit, now what will happen? Magnet itself try to generate opposing H field. And this phenomena we have already discussed in the part 5. And if you have not watched, please go back and watch and then come back to this video. So let's say magnet generated opposing H field, then what will happen? B field is going to decrease, and the B field now it will be somewhere here, as you can see in this image. Now if you do not do anything and just reduce the length of the magnet, opposing H field is going to increase further and B field will decrease further. Why? Just to give you a visual picture of it, let's come to this image. So I have, let's say, this length of magnet. As you can see here, some of the H field or opposing H field is going outside the magnet. Now can you tell me what going to happen when I decrease the length of the magnet? Let me tell you. The amount of H field which is going outside at this moment is going to decrease when you decrease the length. In other words, H field inside the magnet is going to increase as you decrease the length, and finally the resultant B field inside the magnet is going to decrease. And we can conclude that lesser the thickness, higher the demagnetizing H field, and hence lesser the B field. Now focus on the first magnetic material, which is this one, whose coercivity is Hcb, which is lesser than Hc1b of the second material. Let's start decreasing the length of first material till the point where H field inside the magnet became Hcb and finally B field becomes 0. But for the same thickness of second material, still there is a B field, as you can see here, and hence we can further decrease the thickness of second material to get the opposing H field equal to Hc1b, and hence we can say that higher the coercivity, thinner the magnet can be used for a given application. Now this is the last piece of BH curve. We have plotted the BH curve at 23 degrees Celsius and we got the remanence and the coercivity at 23 degrees Celsius. Now if we increase the temperature, BH curve and JH curve going to shrink towards the origin, and hence remanence and the coercivity will decrease as temperature increases. Here you can see BH curve has been drawn at minus 20 degrees Celsius, 20 degrees Celsius and the 60 degrees Celsius, and the remanence and the coercivity at 60 degrees Celsius is lesser than the remanence and the coercivity as minus 20 degrees Celsius. And with this we have come to the end of BH curve of permanent magnet material. And if you are enjoying, please like and subscribe, and see you in the next and last part where I am going to explain about two popular magnetic material.